How's everybody doing? Good. I think I maybe saw some of the groups meeting together to talk about the template that's going to be used for data gathering. Has anybody actually been into the project area yet? Set foot? One person? You're going to go today? Since the assignment was given. Because when you went through before, well, unless last time you went through you were like looking at storm drains. Is that roof drain disconnected? If that was the purpose of your visit, then that counts. Otherwise, I'd love to hear that you've been there again, and it sounds like you've got those plans. So if we just take a look at a couple of announcements here, homework 2 is due on Tuesday, and we're going to do the pond sizing stuff today that will enable you to complete that assignment. But more importantly, stage 1 of the project is due next Thursday. And so what does that entail? Getting together as groups and talking about what standardized template are you going to use to gather the surface data and then actually gathering it. So basically, get a spreadsheet figured out and walk around a 1-block area, spy on some neighbors, see if they've got their catch basins, if there are street level catch basins. You're going to have to identify every place water is going someplace. So if you see a catch basin, okay, there's one here on the map, and then go back to the data later and find out if it's connected to the combined sewer or if it's connected to a separate storm sewer. You're going to have to connect all the dots together and figure out where is the water going. So just stage 1 due on Thursday. Any questions related to the announcements before we talk about stormwater detention? Did everybody get a copy of the notes?
Can I get one more piece on the way?
Was there one extra copy of the notes? All right. I've just got the first homework assignment returned to me, so maybe when you're working on the example today in class, I'll record the scores and hand that back to you. This is a really important figure that illustrates a very important effect. And this figure helps to explain why People's Creeks in West Virginia keep getting washed out and the stream slopes are unstable and why culverts are threatened. It's an effect that's illustrated here, and so it's critical that you understand this and it become a mantra that you could just rehearse on the spur of the moment. Like, you know, if you ever needed to be on an exam that was establishing your minimum competency, for example, this is a figure that might be useful to know if you're in an exam scenario related to engineering that was testing the fundamentals of what you knew. So here in this figure, it's showing, it's a hydrograph. The bottom figure is a hydrograph. And do you remember from our first lecture what a hydrograph is? It's a graph of water, hydrograph, time on the x-axis, and the runoff rate from a watershed, any kind of catchment. So you could have a hydrograph from a parking lot. You know, this parking lot that's right here next to the building, you could measure a hydrograph from that. A hydrograph could be coming off of a very large watershed, like the stream gauge at the New River Gorge Bridge. That could be used to generate a hydrograph that shows over time what flow rate is passing by that stream gauge. And so before urbanization, what you'll know in the comparison of before urbanization and after urbanization, before urbanization, it takes a long time for the peak to get to, for the flow rate to go to the peak. And so relatively longer than after urbanization. If you look at after urbanization, the peak occurs sooner. So there's a reduced time to peak, and also the peak is much higher after urbanization. And the reason for that we've already talked about is because of an increase in impervious area that comes along with development. When you pave roads, when you put roofs, those actions, even when you're just compacting soil, that decreases the infiltration capacity of what was there in the natural condition. And so there may be a cultivated crop that you'd think would infiltrate really well, and it probably infiltrates better than concrete, but it doesn't infiltrate as well as the natural grasses and trees that were there to begin with. And so the two main effects that you can compare before and after urbanization in a hydrograph is reduced time to peak and a higher peak flow rate. Now this graph, you might say is a hydrograph because it's a graph of water, in this case rainfall rather than runoff, but really it's called a hydrograph. And we'll get into a lot more about hydrographs later, H-Y-E-T-O-G-R-A-P-H. So a hydrograph is a graph of rainfall amounts, and this is a little bit blocky. Now, during a storm, it doesn't actually like rain for some constant intensity and then instantly jump up to a higher intensity. Why do you think that this rainfall chart looks a little bit blocky? Okay, it could be an average, yeah. It has to do with the sampling frequency of the instrument. It may be that the instrument is checking the intensity every 15 minutes, and so it's going to assume that you have the same intensity during that 15-minute period, or in other words, an average over a time. And so that's why it looks blocky. Now, the other thing to take a note of here is that there's this curved line, and what that curved line is the infiltration rate. And so at the beginning of the storm, the soil is infiltrating water very quickly. It has a high infiltration rate, but then the infiltration rate is decreasing as the storm goes on, because as the soil voids fill up with water, they're not quite sucking down the water at the same rate as they did at the beginning of the storm. And so look at the before and after urbanization. What it shows is that after urbanization, the infiltration rate is lower. And that coincides exactly with what we're seeing here. If the soil is absorbing less water, in other words, if the infiltration rate is lower, then we're going to see a higher hydrograph peak. It will peak sooner and it'll peak higher than it did before. So what we want to do in stormwater management is try and reverse this trend. All of our best management practices want to increase the time to peak, because when we put in a subdivision and put in a grocery store and a parking lot and a football stadium, all of those things are naturally tending towards the after urbanization hydrograph. We want to try and design features that can push the time to peak to the right and lower the time to peak. So we want to encourage infiltration, and we want to delay the water in its journey towards its outlet. We want to slow the water down. We don't want it to get there quite so fast, because if it gets there fast, it can all pool suddenly all at once. So the next couple of slides, what we're going to be looking at is just what are called best management practices. And the majority of the slides I'm going to be showing you are taken from the West Virginia Stormwater Manual. It was a document just released within the past year that is trying to prepare municipalities for statewide regulations having to do with stormwater. The state is going to be imposing rules to try and reverse the trend of more flash flooding and more property damage due to flash flooding. And so one of the things that you can do is put in vegetated filter strips. And if you just think about the runoff coming from a roadway, if the runoff has to flow over a vegetated area before it gets into a drainage canal here, this is, I think, a sloped canal at the edge of that vegetated filter strip. So if it's forced to flow over grass before it does that, it's going to infiltrate into the soil. Another thing that the vegetated filter strip could be put in next to farmland, and so crops, as far as infiltration goes, is better than asphalt. It's going to allow infiltration, but if pesticides or if fertilizers are applied to the cropland, having a filter strip here acts as a biological filter. So some of the nutrients like phosphorus and nitrogen could be absorbed by the grass rather than getting into the ditch. And you'll probably learn in your environmental themed classes that excess nutrients is one of the dangerous pollutants that are faced by water bodies. So another thing that can have a big impact on stormwater peak rates is simply disconnecting the roof drains from the combined network. And so what's depicted here in this image is previously, presumably, this roof drain went straight down into the ground, underground, connected to the combined sewer and out to a street. Whereas here, to get it away from the foundation of the home, they've put in an extension, and then it just discharges onto the grass. Now, you can add a small rainwater garden at the end of a roof drain, and with putting in special plants and kind of building up a berm here to ensure that the water doesn't flow over the lawn. Some people might have concerns that in a heavy storm the rainwater could erode a certain part of the lawn or cause puddling. And so if you modify the soil here and maybe put gravel underneath this bed of plants and make other modifications to try and improve the infiltration capacity of the soil there, then you can have improved performance. Also, the plants will evapotranspirate water. So in addition to allowing infiltration, they'll promote the evaporation of water. Yeah.
So like how effective are those plants? Because I know at our church, like we have like new pavement.
Mm-hmm.
I think that we're doing, we have to do like a water runoff study for that, like EPA requirements or something like that.
Yeah.
And like instead of like putting like big trough, like we were able to like put like 6 rain gardens in.
Mm-hmm.
Instead, they said that would be enough to like mitigate it.
Yeah. I'm not certain on an absolute quantitative basis how much having plants versus not having plants helps. And it's interesting, in stormwater management, what they do is they have a series of credits. So the regulators don't look at it on an absolute basis either, trying to measure the actual water uptake of a certain plant. What they'll do is that they'll say that you get credit for taking certain measures. And so as long as you get to a certain reduction in volume, then they don't care how you achieve it necessarily. But you can save a lot of money by putting in natural features like this. It's just that some people don't like them because they require a little bit of maintenance. The soil pores can get clogged with silt, and so occasionally something like this may need to be refurbished. The soil could possibly have to be excavated and replaced. Yeah. That's the hope, is to put in soils there that have sandy characteristics, or mix it with gravel so that you don't have standing water for too long. Because you're right, mosquitoes would be very unpleasant. It's a common practice in places that are trying to be green to have strips of vegetated area next to parking lots, and to slope the parking lot so that it goes into this vegetated area. And bioretention means that you're holding on to the water, and at the same time you're filtering out salts, oils, grease, and the nutrients that would be problematic if it got into the watershed. Sometimes parking lots will incorporate pavers or gravel sections that are pervious and allow water to infiltrate, rather than being completely impervious and causing 100% runoff. And there's a video I'll show you that illustrates that effect. This is at the University of New Hampshire. So this is definitely not common concrete. I mean, something's different about this concrete, right? Normally, if you were pouring water onto concrete like that, it would have to find somewhere to go. It would run off to the side or puddle. But as you can see from the close-up, the water in this case is just soaking right down into the concrete itself. And so what does concrete consist of? What's the recipe for concrete when you make it back in the lab? Aggregate, which is basically gravel, right? Different sizes of gravel. What else is in there? Sand, cement, and water. And maybe if you're being fancy, like plasticizers and things like that.
1,500 gallons.
In this case, what they did was they still have the aggregate, you still have the cement, you've got to have water to activate the cement, but they don't add sand. And so what it is basically just a bunch of pea gravel that's cemented together, and it has interconnected voids that allows the water to infiltrate through the pavement and down into the soil. And so if you think about the freeze-thaw cycle, this is a very risky proposition that you actually want water to be going through here, and if it was wet and froze, then it could crack this very easily. So where they use porous concrete like this, they're very, very careful to put a layer underneath the concrete that is very good at draining. So they put gravel underneath it, sand, anything to get the water away from the concrete itself, because otherwise the durability is threatened. But you get a sense that this could be a very effective way at reducing runoff compared to traditional paving. I think, in fact, it's Professor Huffman's intention to try experimenting with this pervious concrete a little bit this semester.
I think we're going to pour some between Morrow and the science building.
Oh, yeah? I just closed the presentation. Between Morrow and the science building, huh? I wish you'd do it just right out here. Yeah. All right, so we just looked at porous concrete. All right. Another thing that's done in these BMPs, as they're called, the best management practices, would be to have a ditch lined with grass. And grass has a higher N value than clay or than concrete. And so what the grass does is it slows down the flow of the water. That's going to reduce the traveling speed of water, and it will increase the time to concentration. And it also promotes infiltration. And so it's going to reduce the volume of water that gets towards the outlet. Sometimes in developments they'll put in special, not ponds necessarily, but they'll design the landscaping to promote infiltration. And so in this case, you can see there's a gravel bed at a low point in the grass that's next to a parking lot that can promote infiltration. This is kind of an interesting idea of a regenerative stormwater conveyance channel that essentially is a series of connected pools. And the purpose of having a series of pools like this is that, think about how steep that channel looks, and it's exaggerated for effect, but if you had a very steep channel, then the water is going to move very quickly through that channel, and there's not going to be very much infiltration. But instead, if you make it a series of terraces, staggered terraces with a small puddle or pond at each one of them, then the water that's in the pond will continue to infiltrate after the storm event is over, and it essentially delays the travel towards the ultimate creek that's illustrated as the outlet here. So it has bioremediation advantages of filtering out whatever contaminants are in the water that's flowing, slows it down, and also is going to be more durable if it's constructed properly than a very steep slope would be where the travel velocities are high. This image is an illustration of rainwater harvesting, and you can actually go to Lowe's in Barbersville and buy a rain barrel with a kit needed to connect it to your roof storm drain if you like. I think they're about $80 or $90 for a big plastic barrel and the equipment. I've got one at my house, and it's nice to have a little bit of rainwater during the summer to water the garden with, but I do calculations when I teach engineering economy that illustrates from the financial standpoint you won't ever make that money back. The value of the water that it holds isn't anywhere nearly great enough to justify the cost of the barrel itself. But still, it's always good to be prepared and self-reliant and those sorts of things. And if it's done right, rainwater harvesting can be a way of reducing the volume that gets into a ditch or is put towards a combined sewer.
How do you get the water through your hose? Like the hydrostatic pressure or just a pump?
Good question. You have to, because the tank's not pressurized, and so at my house I have it on a wooden deck and the garden is about 3 feet below that. And so it flows slowly through the hose. It's definitely not something you could have a water fight with, especially if you take the hose above chest level, then the water's not going to flow in it's not going to flow out of the hose at all. Yeah, so that's a really good issue. Is if you want to take it somewhere else, you're going to have to pressurize the tank or use a pump.
There was a town in Utah that actually made a deal with this
Illegal?
illegal in a lot of the city.
Huh.
I don't know if they solved that or not, but
Yeah.
they were like suing.
I hadn't heard that. Yeah.
How much would something like this cost?
Oh, this one? Well, I don't know. You know, they use rainwater harvesting a lot in Australia, and I think in Australia it actually is cost effective because the value of water in a very arid environment is greater than the value of water here where we have relatively abundant water resources. But I think it could be something relatively simple. You know, about the cheapest tank you can get is a septic tank, where you can get about 1,000-gallon tank for the order of just a couple $100. So this picture, I'm not sure. It looks a little bit more expensive than the plastic septic tanks that people bury underground. A vegetated roof is something that, like all of these measures, is trying to promote infiltration. Except that you think, what's underneath the vegetated roof? It's offices, it could be a hospital, it could be classrooms. And so you have a little bit of a dual mission that you want to keep water out of the building, but you want to promote infiltration in a layer that's above the ultimate water barrier in the roof. And so underneath this roof is probably a very thick plastic liner combined with a traditional concrete roof or what a steel reinforced roof. But above that is soil and plants that are specially selected to have roots that don't penetrate too deeply and specially selected to promote a lot of evaporation. They have a vegetated roof at a stormwater and sewer treatment facility near Cincinnati. That's one of the largest vegetated roofs in the area. It's really impressive to see. And they actually have a tour of the building where you can go and look at the pipes that collect the water from underneath the vegetated roof and take whatever doesn't actually stay with the plants, and they'll ultimately have to discharge the excess. But it will capture the first certain amount. You know, the first maybe ½ inch of rain that falls would be used to provide the moisture needed by the plants that are up on the roof. Sometimes one of the best management practices is identifying locations in a city that are especially polluted. And here it's showing a gas station, and because of people pouring oil to fill up their crankcase or just filling up the gas, the runoff from certain businesses is particularly troublesome to where you'd want to collect it and treat it separately. So here it's showing a collection system that's meant to trap the runoff from this filling station so that it could be treated maybe by ion exchange or at the very least settling to allow the grit to go to the bottom and flotation of the grease and oil to the top. Yeah?
I was in New York City a few months ago, and I noticed when we were at the top of the Empire State Building that almost the top of every building had
Really?
a water tank. Yeah.
Oh, a water tank, yeah, right.
Or pressurizing
Mhm.
water for the building.
Yeah.
That's good. I was making sure that was a water tank.
Yeah.
I spent half my time on the top of the Empire State Building lecturing to my family about what that is.
That's a pressure tank, yeah. Yeah, exactly right. You've got it. That most likely isn't like a rain barrel. It would be to pressurize the water tank. And I'm sure many of you heard about what happened in California when a tourist got into one of those pressurized water tanks in a hotel, fell in and drowned, and was in there for 2 weeks before anybody found her. And it was the potable water source for the hotel, so a lot of people are suing the hotel for like mental anguish and having showered in that water. And so, yeah, you're wincing, and so I get you understand what I'm talking about. All right.
So since they don't have like a water tank nearby or any high hills or anything, they just put it on top of that.
Right. Yeah, yeah. It's either have a water tank or have a pump that pressurizes, and it's cheaper to have and more reliable to have a tank on top of the building. And you still have to pump the water up there. It's just that it doesn't have to be on all the time if you've got a water tank on top of the building. All right, a constructed wetland is a way of artificially restoring an area's ability to provide habitat to fish and birds like migrating birds like ducks and geese really thrive when there are constructed wetlands in an area. But like all the rest of these, you know, the objective is to improve infiltration, to trap water, to slow it down, to give plant contact to the water that's being discharged so that it can take up and deal with the pollutants. A dry extended detention pond is a pond that is meant to be dry most of the time, except for when you have really wet weather events, then the pond will fill up and it would take a while for it to drain. What they'll do is they'll put an orifice, or in this case it could be that it's acting as a weir. This riser here could be that the drain is on the top, and so that water will flow in through the riser only when the water level gets to a certain elevation, but otherwise then it would just be infiltration into the grass that dissipates the water in the pond over time. A wet pond, on the other hand, is meant to have some freeboard so that you could put additional water into the pond during a storm event, but then it's not ever meant to drain completely all of the way. And the advantage of a wet pond over a dry pond is that the dry pond like this can't support fish. It can't support a lot of the same kind of wildlife that a wet pond would be able to if it has water in it all the time. Plus, it's very scenic. People like to have a water view. And so remember, the objective of all of these BMPs, best management practices, is to reverse the trends that are induced by urbanization. And so we're going to be talking about the design and sizing of ponds today. The purpose of designing a pond is to try and mitigate the effects of urbanization. And those effects are an increased volume of runoff, because more of the water gets to the outlet instead of infiltrating. Higher peak flow rates, meaning that the water is able to travel more quickly to the point of concentration, and when it all gets there at the same time, it's overwhelming to whatever constructed feature we're trying to protect. If it's a bridge and all of the water that drains an area that a bridge is going over the stream for, if too much of it gets there all at once, then it can overwhelm the bridge, and the water level will be higher than the bridge deck. People can't drive over it. It can cause damage to the bridge, cause damage to the foundation. And so that gives you an idea of why it would be better for you just to meter out a little bit of water gradually, and if the water was more slow in its transit from its origin towards that concentration point, the situation would be a lot better. We also want to try and avoid the environmental degradation that comes from a variety of different pollutants that are found in urban environments. So we want to make after more like it was before. And so we can do that at the source by mandating that a new development dispose of their water locally. You know, instead of allowing a company to discharge its stormwater to a ditch that's near their business. If you force them to deal with it themselves and not just make it somebody else's problem, then that's going to save the downstream, save having to treat it downstream when the problem actually gets magnified and concentrated by so many other people doing the same thing. Downstream control is when, instead of, or maybe in addition to, trying to control things at the source, you are somewhere after multiple streams have combined trying to detain it, slow it down, or your last chance for controlling the excess flows at the wastewater treatment plant, where they may put in a gigantic flow equalization basin so that they're not forced to discharge to the river without treating the wastewater first. So here's a cross-sectional view of an extended detention basin. Now this is the one that doesn't have water in it all of the time. And if you look at some of the features that are here from a hydraulic basis, what you have is an outlet that is essentially governed by the orifice equation. There's going to be some water level, and we know that the orifice equation is that velocity is the square root of 2gh. Remember, v equals the square root of 2gh, where h is the distance from the water level to the center of the area in the orifice. And of course, because of energy losses, we put in a coefficient of discharge, C sub d, and we dealt with those in the labs last year. And if we want to know Q, the flow rate that will come out, then we say it is the coefficient of discharge times the area times the square root of 2gh. And so the orifice equation governs the outflow from the outlet. So water comes in to the pond at whatever rate is governed by the watershed. The watershed says, well, and the rainfall. You know, if it's a big storm and urban watershed, we're going to have a big peak. But the point is that this runoff hydrograph, whatever is running off from the catchment, is what comes in to the pond, and what goes out of the pond depends on what we engineer into the structure. We can govern the outflow rate by how big the pipe is, or we can govern the outflow rate by how deep the pipe is located. You'll notice here that there's also what they're calling the primary spillway. When the water level gets up to this elevation, then it starts pouring into that pipe, and it's acting as a weir. And then the emergency spillway is just if the water level rises even further, it would go over a low point in the dam. Now, this is a cross-sectional view of a dam. They would probably have, you know, the dam is having a low point somewhere, so that normally the water level is here, but if it rises even further, it would go over a part that maybe is more ruggedized. This low point is ruggedized compared to the rest of the dam, so that if water flows over it, it's not going to completely erode the structure. Usually basins like this have the advantage of allowing particulate pollutants to settle into the bottom of the pond. And that's a good thing because it means they don't get into the stream. But then it's a bad thing because those particulates, if they're not removed from the pond periodically, then that's going to reduce the infiltration capacity of the pond. The other kind of pond would be a retention pond. So detain means temporary. Detain, if you're detained by the authorities, that means they just hold on to you for a little while. You spend the night in the drunk tank if you're being detained. But if you're being retained, that's a more permanent thing. So a retention pond is something that permanently has water in it, as depicted here. And so in this case, the way that they ensure that the pond always has water in it, if you compare in this one, the outlet pipe is going to have a perforated riser at all the way through from the bottom to some elevation up here. But in the retention pond, they have this pipe is all enclosed, and then the riser is perforated some elevation above the bottom of the pond. And so where you have holes in the pipe governs what the water elevation is at. And this pipe right here isn't open to the pond. In the previous case, in this case, you could have the outlet open to the pond at the bottom of the pond. But in the case of the retention pond, it's not. And you'll usually have a longer detention time, a longer, in this case, retention time. You'll see the retention time is 2 to 4 weeks rather than 24 hours in the detention pond. One of the environmental risks is that anoxic conditions, that means in the absence of oxygen, if the pond is really deep, then it might be that at the bottom of the pond there isn't enough oxygen diffusing from the surface layer here, and there can be a sludge layer and bacteria that break down organic pollutants in the absence of oxygen, and it generates a really foul odor. And so usually there are guidelines from municipality to municipality of how deep a retention pond should be, and it varies on a lot of factors like the water quality and maybe the adjacency of other buildings and developments and how big of a problem it would be if it smelled bad in the area. So how big should the pond be? The pond size needs to be the difference between the outflow and the inflow. Now, this hydrograph that's shown isn't the before urbanization, after urbanization. It looks similar. It has the same shape, but in this case, what this is the big hydrograph is the water coming into the pond, and then the smaller curve, the lower curve, is the outflow hydrograph. And so it's doing what we want it to do. It's lowering the peak flow rate, and it's shifting the peak time to the right. It's lengthening it, so it's behaving as we had hoped. But the size of the required pond, you can see, is the difference between the in and the out. Have you ever done anything like that, compared in versus out, and then sized a reservoir based on that? When did you do something like that? In the project, right? All right, so think about the project from last year. The design project that you did, you were sizing a tank. What was the constant and what was variable? You had an in and out. One of them in the project was constant and one was variable. Okay, we assumed the in was constant, and it was just, there's some spring that magically always sends the same amount of water, the same flow rate into your tank, and even more magically, it is equal to the average daily flow rate on the peak day. Right? So anyways, it was constant. The outflow was variable. What governed the variability of the outflow in that pond from the project last year? Why was it variable? Yeah, people are using varying amount of water. At 8 p.m., they're using more water as they do dishes, laundry, take showers all at the same time, versus they do their laundry and dishes in the shower, is what I mean. So they're using water at a variable rate, whereas in the ponds that we're designing right now, all right, we're going to be designing a pond. We'll put in a little orifice here. We'll put in like an emergency riser. Here's the perforations. Water comes into the pond. So here's the water coming in. Okay, so in is variable. In is variable. Why is it variable? Okay, during a storm, it's not always the same amount of rainfall. It may be raining a little bit at the beginning of the storm, then have a period of really high intensity, then it'll start tapering off, so variable rainfall intensity. And then it also has to do with travel time. At the beginning of the storm, the only water getting into the pond is the water that rained close to the pond. But after an hour, the rain that's a little bit further away has finally made it to the pond. And so it's partly about travel time, and we're going to get into a lot more depth on the travel time issue later in the semester. But it's important to know that the inflow is variable, and so you can look at this hydrograph and see that the flow into the pond is varying, and then the flow out of the pond is also varying. So the outflow, why is the outflow varying? It's the depth. Yeah, as the water gets deeper, so if the water is all the way up here, then H is big. And the orifice equation is the square root of 2GH. And so the deeper the water, the greater the flow out from the pond. And so at the beginning of the storm, hardly anything is flowing out of the pond because there isn't very much depth quite yet. So the process that we're going to follow to size the pond is, in a best case scenario, we'll have an inflow hydrograph that tells us how much water is coming in at certain times during the storm. So we'll have an inflow hydrograph, and then we'll calculate the volume in during the time increment, and that's going to feel very familiar to you. You're going to be saying the volume that came in was the flow rate during the period times 3,600 seconds per hour, so that's the volume in. And you're going to calculate the accumulated volume, and that will be, well, how much was there in the pond last hour? How much is in the pond now? The accumulated volume in is how much there was in the last hour plus how much came in minus how much went out. And so you're just doing a flow balance. Accumulation is in minus out. This is one of the most powerful equations that I know, and it's so simple that accumulation is in minus out. And so we're going to be looking at how much water is in the pond on an incremental basis. We'll be integrating over time in 1 hour increments in the case of the example we're going to do in class. We'll be looking at in minus out. And then we'll find out for how much volume there is, what's the pond height. And then if you know the pond height at that increment, then you can say what the flow out is. And you're going to use the flow out in the next hour when you move the road down. Once you set up the spreadsheet, it's the sort of thing that you can just drag all of the formulas down and it solves itself. And it's not even iterative. You don't have to make it converge. None of those crazy things that we had to do in hydraulic engineering to get our spreadsheets to converge, we don't have to deal with any of that this semester. It's all going to sort of happen on its own without us having to guess. So here's an example. I'd like you to start up Excel and type in the inflow hydrograph that I've got written on the screen there. So the very first columns on your spreadsheet are going to be time, inflow, and this is cubic meters per second. And then we'll talk about how to simulate a pond that is 65 meters by 65 meters. It has vertical walls on it, just to simplify what volume we've got for certain water heights. And then we're going to try and find out for this pond what will be the peak flow rate and then how long it will take to drain the pond. You need to have these numbers for a while. I'll leave this up. I won't disturb it quite yet. Give you a chance to type all that in. Did the laptops log in with your credentials, or did you have to use the crazy password again? Huh. What was it? STRACITE. See those numbers there? Yeah, all right. I'm going to switch to, I'm going to turn on Excel. Ugh. Time. Well, geez, why would I type it when I could just cut and paste? I wonder if there will get, you know, Google Glass, those goggles that they've got. I wonder if there will ever be a time when you can just like look at something and then it will do text recognition and start a spreadsheet for you. That'd be great, right? All right, so this is our inflow, and what did we say the area? Well, we'll do length in meters is 65, width in meters is 65. The characteristics of the pipe has a diameter of 250 millimeters and a C sub D of 0.59. Okay, so diameter of the pipe is 0.25 meters. From that, I'll calculate the area of the pipe. It's equals 3.14159 pi d squared divided by 4. And the C sub D is 0.59. All right. So I'll call this area of pipe because I'm also going to have an area of pond. And that'll just be the 65 times 65, of course. All right, so we're going to have the volume in, and that's going to be cubic meters. And the volume in during the first time increment is going to be 0. Nothing's happening, right? Then there's going to be a column that is our accumulated volume column. Okay, so accumulated volume, and that's cubic meters. And if we want to find out what's the accumulated volume is, at this time, what's the total amount of water in there, we're also going to want to know the pond depth in meters. Like how deep is the water? I guess I should say water depth, because that's going to vary. The depth of the pond won't vary. Its geometry will remain fixed. And then there's going to be H. How is H different from the pond, from the water depth? If we go to this figure here, well, let's look at it here on the drawing from the screen. If there's water depth and H, they're going to differ by just a bit. Half the diameter of the pipe, right. Assuming that the pipe is at the bottom of the pond, which we'll assume that. We don't want there to be a puddle in the pond. So we'll put the pipe at the bottom of the pond. So the next thing we need to have in our spreadsheet is H. All right. And then for this depth, then we can calculate the outflow. And that'll be cubic meters per second. And then we can find out the volume out. During the time increment. All right, so we may need to change some of the column headings along the way, just sort of spitballing this, but let's see. The accumulated volume is going to be the inflow, the volume in, well, it'll just be 0 for the first one. We'll change it to include a formula on the next row. The water depth is just going to be 0. The height will be 0. The outflow, all these are 0. All right, during the first hour, what's happening? We've got flow in, and so the volume is going to be this flow rate, cubic meters per second, times 3,600, because there's 3,600 seconds in an hour. The accumulated volume is how much there was in the pond during the last hour, plus the water that came in, minus the water that came out during the last hour. Why am I going to the last hour instead of doing the volume that went out during this hour? Because I don't know how much went out yet during this hour. I have to lag. And this is, it's an error source to be using the flow rate. Essentially, this out component is using the flow rate during the last hour. But the more time increments you have, the less important this error is. And so it's good to have high resolution data because it maximizes your accuracy. So what I did in that formula was I said accumulation is in minus out. Basically, what it was previously, how much is in the pond is what this cell is answering. How much is in the pond is what was in the pond last hour plus what flowed in minus what flowed out. Any questions so far? All right. Our water depth is going to be the volume in the pond divided by the cross-sectional area of the pond, and I'm going to anchor my reference up there to the pond area. And reduce the number of digits because it's just distracting to have tons of extra digits shown. All right, H is going to be the water depth minus half of the pond, the pipe diameter. So pipe diameter, anchor that reference, divide by 2. Because I want to subtract, if I've got the depth of the pond, So this is pond depth. So from the bottom of the pond up to the water surface, H is pond depth minus pipe diameter pipe divided by 2. So that's what I've just typed into Excel. Again, I'm going to reduce the amount of digits that are shown. Okay. How much water is going out right now? Okay, I'm going to do equals. The formula that we had before is written on the board. Q is C sub D, area of the pipe, square root of 2GH. So C sub D, remember I am going to put this recording online, so if you get lost along the way, you'll be able to refer back to this video later on if you like. Okay, so C sub D times the area of the pipe, also anchoring that reference, times the square root of 2 times G, 9.81, times H. Not anchoring that. I want that to change every time I drag that down. So this is the flow rate out. When I display fewer digits of on screen, it's not eliminating all those extra ones that were there before, it's just not showing them. So it retains all of the precision internally. Volume out is going to be the outflow times 3,600 seconds per hour. So that's how much flows out if you've got a flow rate out of 0.005. So let me walk through it one more time. We'll talk about each column. The inflow column, that's given. That's from a hydrograph. You get inflow from a separate analysis. Before you size the pond, you have to get the hydrograph that's coming into the pond. Okay, volume in is just the inflow times the time increment, because we're doing this on a 1-hour basis. Accumulated volume, that's how much water is in the pond. That is how much water was in the pond during the last hour, plus what came in, minus what went out. What went out during the last hour. And the reason why we can't do it what went out during this hour is that what went out this hour depends on the volume inside the pond. And so it would be some circular reasoning there. So we have to step back to the previous hour and calculate it for that. So now that I've got the water depth is simply what's in the pond, the volume divided by the area. The height is water depth minus the half the diameter of the pipe, and then outflow square root of 2GH is what it's based on. Let me just drag this down and see where things are at. What do we expect? We expect as the water depth increases, we want to see, as the water depth goes out, we'd expect the outflow to be increasing. Well, let's look at the figure. The typical figure here, this, shows that the storm comes, it peaks, the storm starts decreasing, so the pond comes to a peak, and then the outflow from the pond starts decreasing. What do we see in our behavior? So the storm peaks here at hour 3 at 0.81 cubic meters per second. What about the flow out of the pond? It's going up, and it looks like it has peaked. And maybe we can show a little bit more precision here to know precisely during which hour it peaked. All right, it peaks during hour 5, and then it starts declining. And so the question that was posed in the example is, what will be the peak flow rate out of the pond, and then how long will it take to drain the pond to 10% of its peak volume? So how long until we see the peak in the pond? The peak happens 5 hours. Compared to the storm was 3 hours. And then how long does it take for the pond to be drained to 10%? How full is the pond? What's the fullest point of the pond? It's here during hour 5. It gets up to almost 8,000 cubic meters. Well, if we continue this time increment, Okay, and we still have 0 here, 0 there. We'll continue these calculations and find out what's happening to the pond. The pond will continue to drain. So if you look, the water depth goes up, and then it's going to be declining. We want to find out when is the water level in the pond approximately 800 cubic meters, because that's when it's 10% of what was there in the peak. So it's down to about 800 cubic meters sometime between hour 23 and hour 24. All right. Any questions about this example? Now, the really powerful thing about having a spreadsheet like this is it allows you to play around with the numbers. What if your regulator said that you're only allowed to have an outflow equal to 0.1 cubic meters per second? What could you do to limit your outflow to 0.1 cubic meters per second? I can think of 2 things. What's that? Decrease the diameter of the pipe. So if you make the pipe smaller, then it's going to be restricting how much can go through the pipe. And so, exactly right. If we change the pipe diameter from 0.25 to 0.125, then the outflow, the maximum outflow right now is about 0.17. Now it is less than 0.1. And so the power of the spreadsheet is it allows you to play around with the design. What if you use 0.2? We're getting close. 0.18. All right, so we're almost there. This is a way of us to find out how does the pond change when we adjust the feature. And so what would be the other way besides restricting the diameter of the pipe to make sure that the outflow doesn't get any larger than 0.1? Part of its part diameter. So outflow, Q equals C sub D A square root of 2GH. So we could change the area of the pipe to reduce the outflow. What else could we do? If you make the pond area bigger, it's going to decrease the depth. Exactly right. So let's have it still be a square pond, but instead of 65 by 65, let's say what if it was 80? So we change it to 80 by 80. How is that going to change the peak flow rate that we're seeing at hour 5? All right, it decreased it. If you make the pond area bigger, the depth is lower. That means that there's going to be less head pushing water out through that pipe. So that gives you an idea of how to design a pond. The things that you can control, namely being the pipe area and the pond area. That is the ideal approach, is to have a runoff hydrograph of showing what's coming into the pond. There's a simplified process, AASHTO developed, when you don't have that information of a full hydrograph. If all you know is the peak flow rate, so if you know Q sub P, then what you do is you assume a triangular hydrograph. You just assume that the water goes from 0 and it reaches the peak and then it comes back down at some time called the base time. And you have an outflow hydrograph that comes up in a triangular way up to the peak flow rate out of the outflow hydrograph. And so this approach, the AASHTO approach, is used when you don't have an inflow hydrograph for a pond. And the AASHTO method depends on calculating the ratio of the storage volume and the volume that is actually going to be based on the amount of water that has to be retained. And so it's an empirical equation. It's not fundamental, but we'll illustrate how to do the AASHTO storage volume using the same example as before, the same setup as the previous example, but put into these equations that are shown on the screen here. Let's consider what if we had some storm where the time to peak was 3 hours, and that's the same as our last storm. But what we're going to be doing is we're not going to be considering the other data points. In this storm, we had a full hydrograph, but in the example for the AASHTO, we're just assuming that it goes from 0 to 0.8. It's going to have, in other words, a triangular inflow hydrograph. Okay, so we've got a QA being the outflow hydrograph of 0.14 cubic meters per second. And the volume of runoff based on the duration of the storm. We know that the volume of runoff is 9,504 cubic meters. And so how big should the pond be? So the volume of storage of the pond, if you look at this shaded area, the pond size depends on the difference between in and out over time. You don't want to make the pond big enough to hold every single liter of water that flows through it. All you need to do is make it big enough to hold the water difference. Like going back to the project that you did last semester, you didn't make your storage reservoir big enough to hold all of the water that's used in the town during the whole day. You only make the storage pond big enough to handle the difference between the inflow and the outflow. It's not big enough so that you assume that there's no inflow into the pond during the entire day. Okay, so here in this example we've got T sub P is 3 hours, T sub B, 2 T sub P minus 0.05 QP divided by QP. Okay, so that's 2 times 3 hours minus 0.05, 0.81 cubic meters per second, 0.81 cubic meters per second. So the T sub B is going to be 5.95 hours. The volume of storage is the volume of runoff times 1.29, 1 minus QA divided by QP to the 0.153 power divided by T sub B divided by T sub P to the power of 0.411. Okay, so the V sub R, the runoff volume, which we calculate just by integrating the hydrograph, the runoff hydrograph, is 9,504 cubic meters times 1.29, 1 minus 0.14 cubic meters per second. That's QA that's given in this problem, the flow out of the pond. Q sub P, 0.81 cubic meters per second. And that's to the 0.153 power divided by 5.95 hours divided by 3 hours to the 0.411. Okay, so if you calculate that, you get 12,260.16 times 0.9714 divided by 1.325. So that's all equal to 8988 cubic meters. So that's the volume of storage that's required if you take into account the difference between in and out. How big should the pond be? You've got flow coming in, you've got flow coming out. You don't have to make the pond big enough to store all of the water that comes in, because at the same time that water is coming in, water is also going out. It's just that it's going out of the pond slower than it's coming into the pond. And so the pond level is going to rise, and it's going to stop, and then it's going to begin to drain. All this is a simplified empirical approach to use for calculating the required pond volume when you don't have a full-fledged hydrograph for the inflow. Now, how does this compare to what we were doing in the previous example? In the previous example, we found that the required volume was approximately 8,000. Let's take a look at the spreadsheet again. Okay, in the spreadsheet we saw that the required volume, if it is a 65 by 65 pond, then the required volume was approximately 8,000 cubic meters. And remember that there are some differences here. In the example that we worked before, it wasn't a triangular hydrograph. But the AASHTO approach assumes a triangular hydrograph. It's a good, quick and dirty way of sizing a pond if you've got no other data to go from. Any questions you want to ask for that example? Okay, with the pond sizing exercise we did on Excel and this illustration of the AASHTO equations, I think that you've seen all that you need to see in order to do the homework assignment that's due on Tuesday. Let's just review before we finish. All right. When water is coming in due to a storm, you can store it locally, meaning try and promote infiltration, percolation, the porous pavement video that we saw. You can somehow, right at the site, deal with the problem. Or you can move the water a little bit, but you try and reduce how quickly it gets into the network. So if you have rooftop storage of rainwater due to like a vegetated roof, a green roof, that's an example of inlet control. Or if you have underneath a parking area, you can put a stormwater detention pond underneath a parking area, just like an underground buried tank that fills up with rainwater. On-site detention might be a ditch or a pond, a dry or a wet pond, meaning either like a retention or a detention basin. Or you could even have a concrete basin, something that's not going to have any infiltration but is strictly for storage. And then inline detention versus offline detention are both illustrations of downstream storage. So that's not controlling the problem at the source, but that's once the water has sort of accumulated from several different sites, trying to engineer some sort of a solution like the Japanese did. Remember the video that we watched of those gigantic caverns? That's an example of offline detention. They're moving the rainwater from Tokyo to those gigantic underground caverns, and then they're pumping it out of those underground caverns using those jet turbine engines. Ultimately, water will make its way in a combined sewer towards a wastewater treatment plant. And so wastewater treatment plants have organisms. It's based on biology. You're actually using bacteria to break down the pollutants in wastewater, and you can't turn that up and turn it down like you're stepping on the accelerator of a car. I mean, you can make a car go from 0 to 60 and then make it stop again very quickly, unless you're driving a Prius, then it takes a little bit longer. But the point is that mechanical systems can be taken from stop to start and stop again very easily, but biological systems need a more gradual inflow. And so part of the reason why we're so anxious to have a gradual volume of water going towards a wastewater treatment plant is that what's purifying the water can't have a lot of variability. It can't handle it. So some things we can do is we can lower the C value by putting in vegetated features. We can detain the water where the precipitation occurs, or by pooling the water from a single development into ponds. So we already took a look at some of the pervious pavement, and this is a cross-sectional view of the water flowing through that aggregate that doesn't have sand in it, in between the voids in the aggregate. Here's a picture of how you could have detention underneath a parking lot. It could just be a series of storage tanks that makes use of the otherwise unused area underneath a parking facility. Here are a couple more pictures of ponds, and ponds can be made to look pretty nice. You know, you could put a couple of ducks in there and put plants, and it's a pleasant thing that people will enjoy. Inline detention would maybe be a storage vault that has a large volume that water can be directed towards the storage vault during periods of heavy rain. And this is a flow equalization basin at a wastewater treatment plant where all of the incoming sewage is just stored so that when there's a big glut of water coming all at once to the treatment plant, they can store it and then over time gradually treat it rather than having to just dump it straight into the river because they can't load it into their holding basins all at once. Okay, so let's just finish off by taking one last look at the announcements and remind ourselves what's going on. The homework assignment's due on Tuesday in class, and I hope that you'll get a chance to go visit the project area over the weekend and start gathering the information that each group needs to develop for the submission a week from today. On Thursday the 12th, we're going to talk about stage 1 and get the surface data all collected. Any questions? I'll see you on Tuesday.